Alright, what's good, y'all? So, I have a deliverable due today. I have to finish the control unit, but problem is I forgot one instruction, and that is the XOR instruction that we actually need to use. So, I need to edit the ALU control unit, and the actual control unit. And then, on top of that, I can finish up the top level, and then we can be ahead for next week. So, oh, did I do XOR? I might have deleted it, actually. No, XOR is 0110, right? Yes, it is. So, when we have the opcode of, where's XOR? Oh no, this is the func, isn't it? No, it's not. It's the opcode. Oh right, it's an R-type instruction. This is the ALU control unit. The ALU control unit does take in the func field. So it's meaning when it has 0 or 110, then we do 0110, because that is our XOR. Yes. So that's good, because I replaced it in a way where it's a bit easier. And then we have what else do we need to change? So let me mark that as done here. Oh wait, not the control unit, the ALU control. So for the control unit, this one has to change two things. Where's the control unit? There it is. So 110 func control unit. So the R type doesn't need to change, it's the I type, because I added an I type instruction. So default. Oops. Alright. So the question is it default? Because if it's default, then it's fine. So we have named I. So for this we are going to write to the register. We are not going to jump, we're not going to branch. We're not reading from memory, we're not writing. Oh wait, mem to reg is this mux. So that will be 0 because we're taking the ALU results. So, and then we are doing an ALU operation. We are not writing to memory. ALU source is 0. Oh no, it is 1. Yes, it is 1. And then reg writes. We are ready to reg. Okay, so it's just default, so it's fine. Alright, cool. So we're good on that. Oh, it is more simple than I thought it would be. Alright, cool. So now I can finish this. So the jump address. So I thought about this. Check up on jump address and okay, so what this is trying to say, I had it labeled wrong. So the full jump address is for our 16-bit CPU is going to be is program counter plus 2. Program counter plus 2. And this part is program counter plus 2 is our bottom part. So this is going to be the upper bits. So that's going to be 15 down to it's upper 2. So it's 15, 14. So, because 15 and 14. Yeah, let's just say and. Like we're... Or no, it would be or in this case if we're adding them together. We can just say plus, I guess, in this case. And then it's the immediate shifted right or left once because we're multiplying by 2. And then this is 13 down to 0. So, in this case, oh, that's the other thing I need to do. The shifter, shift 2, this needs to be shift to left. So we don't even really need that part, but let's keep it because we need it later actually. Shift, let's call it left shifter. Right, and then this one, right? I don't. The output is. The input is this is 11 down to 0. You shift it left twice, so you have 13 down to 0. So this would be 13 down to 2. 13 down to 2 is input. And output gets the value of padded input. Oh, I see. Yes, but this is just going to be 13 down to 1. 12 down to 1. Because we only shifted once. 12. Wait. That's not right then. Part over 2 bits. Number 4. 11. And then you have 13 and 14. But that's not right. What am I missing here? So you have 25. Because you chop off the opcode. That gives me 11 down to 0. You shift once, that's 12 down to 1. Let me think. Because this is not adding up for now. $25. Right, so so it's 6 bits. This is, yeah, because that would be 31. So it's nice. So it's the opcode, so it's 15. Yeah, so it is 11. Plus 2. This might just be the upper portion, which is 3 instead of 2. So immediate in that case would be 12. Then you shift once, so negative 13, and that'll be 2. I think this is right. In the sense where you definitely take 11 down to 0. Our word size is 2. So you shift to left once. So now it's 12 out of 1. And then that would be the lower chunk. It's 12 out of 1, and then you have 3 left. And that will come from the program counter. Alright, let's go off this assumption for now. So I think that's right. And then that would fix the top level. And then for our shifter, so now the input of that mux would be that. So now we have the jump address. And then we want to calculate now the branch address. Right. So we now calculated this, and we want our adder. Yeah. So we have this 2 adder. 2 adder has C out of 2? Yes. Alright. Oh no, we gotta shift it first. So we could say branch address shifter calc is left shifter with the port map of input is the sign extend output. And then we have the output, which is I'll definitely need to, I don't think I did that. And then this is 16 bits. I'm just gonna slap it right here. Oh boy. Oh, there we go, fix itself. Alright. Let me make sure the linter does its thing. Alright, cool. So we have that. And then we have our branch address adder. And this is an adder. Oh shoot, I copied that. Right. And then port map where bus A gets mapped to the what did I name this? Jump address. So this is coming out of the two adder. So we have jump, no, two adder output, and then we have bus B, which is the branch address shifter output, and then we have result, which gets mapped to we could just say branch address. And then we have couts, which is just open because we don't care about this. All right. So now that we have the branch address, we now need to connect the two with muxes so we can select. But yeah, so where's a mux example? That's a terrible mux example. Let's do this. So we have the branch mux. This is a mux where the control is branch sig and zero sig. Let me put this in parentheses. Right, and we have top in, which is the two adder output, and we have bottom, which is the branch address output goes to right. Uh-oh. 0 sig is not declared. Okay, what do I call it? ALU 0. ALU 0. And then what's next? Control is not. Oh. Oh. Well, it figured itself out. Alright, so we have the branch mux. And then we want the. Where this comes from? Jump mux. This is mux. Port map. Control. Gets mapped to. Jump sig. And then we have the top in, which is the jump address. Did I name it that? Jump address. Wait a minute. Jump address calc left shifter. 0. Can I say then that branch address adder? Yeah, I just skipped that. Can I just say that then jump address gets the value of branch address shall extend. Oh wait, sorry. Jump address shifter output from 12 down to 0, or jump address. Oh wait, this is also going to be 12, 0. Well, then I could just say this is whatever. Oops. Right. And then say that this is 15 down to 13 is is the 2 adder output 15 down to 13, and the jump address goes right here. Right. And then type in jump address, and then the bottom is the output of that mux. So it's branch address mux output. That thing is kicking. And then the output goes to, what did I say for the program counter? Read address is PC input. Goes to PC input. What is this? Oh. And then what is this one? It's neither oh. Branches does exist, right? Yeah. Why can't I do that? branch and. So we can say back to branch sig and ALU 0, and then this is going to be branch and. So let's take this up top. All right, and then I think that's it. All right, cool. Let me double check this. Yeah, because Zor will be the same, because that's a R-type instruction, which should all be the same. All right, so I think we're cool in median jump. R-type. All right, awesome. I am good on this deliverable.